So we took some notes together in class on significant figures, and if you missed those or need some reminders about them, then this video is the place to get them. And I just wanted to start with this agenda because this is also kind of how we're structuring our notes. We're going to do this in two parts, and I'd encourage you to do the first part of notes, stop, pause, go and do the problems that it matches up with on page 10, and then come back after you're sure you got those basics down, and we'll do the second part of notes together, and then you can go and finish out page 10 problems, because those were homework or are homework if you did not finish them completely. So let's get going on page 9, and this is going to be all of it, like I said, just in two parts. And first we have to actually know what are significant figures. Even that top part, it's the basics, but nowhere on there does it actually tell you what significant figures are. So first off, I'm probably going to, or already am, calling these SigFigs. I'm almost never going to say the entire words out, significant figures. So if we're talking about SigFigs and you're not sure what's going on, that's what this is talking about. And it might be worthwhile writing this here at the top of the page so that future you can come back once SigFigs are confusing or scary and find out where those SigFig notes were. But as for what is a significant figure, well, it's just the important digits in a value. So which one of these digits add to the accuracy and the precision of our measurements and help make it a better measurement. And that's really the first thing about SigFigs, is that better measuring devices have more SigFigs. Now, in class, we had some examples in our bell ringer that talked about SigFigs a little and got people's ideas of SigFigs before they even knew what they were. But if you look at these two scales, we can very easily tell which one is the better scale, the one that's probably a lot more expensive because it gives us more digits, more significant figures. And hopefully you agree that this scale on the right, because it gives us 3 decimal places, and this one can only do 2 decimal places, a whole lot more total numbers even here, than that right-hand scale measuring the piece of chocolate is the better scale. And in terms of measuring and taking measurements, when we read numbers off of a display like this, you need to make sure you record your measurements straight from the scale. Just read it off, never ever round a measurement that you're taken or given like this. Now, like we said, better measuring devices have more SigFigs, but you can't always just tell those SigFigs by looking at the numbers on the jar, or on the beaker or the graduated cylinder, whatever it is. So you're probably going to have to pay a little more attention to the measurements that you're taking here. And both of these containers have numbers and lines on them that we have to interpret and kind of figure out what is this volume that we've got here. And in our bell ringer, we practiced making these measurements. And the thing to remember first and foremost is that we always are going to record our measurement on a type of glassware like this where we have numbers and lines. We're going to record 1 decimal place farther than what the device is labeled as, 1 more than you can read straight off of the label. So when we look at this first example, notice that my water line is between the 2 and the 3 line. So when I'm thinking about what number I'm going to be recording, that answer, that number measurement is going to be between 2 and 3. And even though there's not numbers on them, if we count, there are 9 lines, meaning 10 increments, 10 chunks, between the 2 and the 3. So that tells us that each of these lines is 0.1, 1/10 rather, of a milliliter. So we've got the 2.2, 2.3, 2.4, and the big line in between is 2.5, which means as we look closer, our value now is between 2.6 and 2.7. So we're going to add on to that measurement. It's at least 2.6. But we can tell when looking at this that this water is not exactly at the 2.6 or the 2.7 level. It's in between. Now, some of you who might be saying, well, up here it goes to 2.7. We don't read from the highest point on the curve. This is what's called a meniscus, the fact that water curves up towards the sides of its container, especially if it's glass. We always read from the bottom of the meniscus, not the top. So this is between 2.6 and 2.7, and we have to interpret what we think that next digit is. The equipment is not designed to tell us that. We have to use our best guess, our best judgment there. So in my opinion, it goes a little bit past halfway. So you might say that this is 2.66. I think it might actually be, in my opinion, a little closer to 2.67. So that's what I'm going to agree on or decide on. If you disagree, and in a lab, if you disagree with your partners and you think, no, that's 2.66, not 2.67, I don't know what they see in there, you write down your digits. Everyone's interpretation of that last digit is their own thoughts and feelings on it, because there's no label there on the device to tell you what that level is. But we always need to do that. We need to interpret one place farther than you can read straight off of that measuring device. Now, I put this second picture in here mostly to hit home something weird that happens with our chemistry glassware, is sometimes we have numbers on both sides of these lines. And that's because sometimes chemists care, most of the time, we care about how much stuff we poured into this beaker, this container. But sometimes if we fill the beaker up to the top, then we can use these other lines to measure how much we pour out. And the way to tell the difference is where your zero is at. If I have poured 0 liquid into this container, then my 0 line, my water, that is non-existent, is down at the very bottom. And similarly, if I put in 1 milliliter, it's going to be all the way down here at the bottom. If I think of my 1, which here, 250 to 200, 150, 100, then I'd have my 50 and my 0, there's no reason why 1 milliliter in, one barely little drop, would fill this all the way to the top. So when you're looking at any devices that have more than one set of numbers, and most of the time, like I said, we're trying to figure out how much is in this beaker, then we're going to read it off of the side that has the 0 at the bottom. So that being said, I've now gotten my answers narrowed down, but still, my line, my green liquid, is somewhere between 50 and 100, and it's pretty close to this middle line. But since there's only one line between 50 and 100, then that is our 75 line, which means that these increments between lines, between what we can actually read off of the device, are 25 milliliters wide. So that is to the nearest 10, or not even the 10, even bigger than that. But because our measurements are every 10 plus, then the closest we can approximate is to that next place, to the ones place. So we need to interpret how close is this to 75. And if I get rid of all my markings, which make it hard to see, I think that's slightly below. I know that we have this kind of wide band here. And you might be saying, no, this is definitely above. I can see that dark edge of that lighter band up above the 75 line. Remember that we only read from the bottom of the meniscus, and this kind of band that you're seeing here, this lighter kind of edge above the rest of the darker colored liquid here, that's the meniscus. This is just in 3 dimensions, so that's the water pulling up to the glass that's staring at you, facing you, which is why you're seeing that wider band there. So that's what it looks like in real life. And so we need to practice and make sure that we're always reading from the bottom of that band, kind of where the darkness of that liquid starts. So that's definitely below 75. So I'd maybe call that 74 or 73 milliliters. That's about as precise as we can get. If you're like, no, that's clearly 72, that's your prerogative. You choose 72, you use it, and you go with it. So we are and will continue to practice making measurements throughout the year, but while we're talking about significant figures and why numbers are important and doing math with numbers, I want to make sure you know kind of why we care about all of this stuff on paper. And it's not really because it's a big difference on paper, it's because it makes a big difference in our measurements and how carefully we're measuring things and what our results are. So the actual notes part of things about, okay, I'm looking at stuff on paper now. I've taken measurements. How can I tell how good they are? How many SigFigs they have? So this is where we have some rules for counting significant figures. Now, the first rule is the most important, and it's the simplest. Anything that is not a 0, meaning 1, 2, 3, 4, 5, 6, 7, 8, or 9, is always going to count as a significant figure. So if it's not a 0, you should have no doubt as to whether it's significant or not. It always will be. The only questions about whether it's significant or not is going to come from our zeros. There's actually 3 different types of zeros, and the rules for whether or not they're SigFigs are going to depend on what type we've got. So the first type are leading zeros. These are zeros to the left of all of our other non-zero digits. So here you can see these zeros are before the other numbers that are not zeros, left side of them. So those are leading zeros, and leading zeros never ever count as significant figures. As much as you might argue that they're important, that if I got rid of them, then 25 is a completely different number than 0.0025, I don't disagree. They are important for holding place value, but that doesn't necessarily mean that they're SigFigs. I could technically get rid of those zeros using scientific notation, and we'll talk about this and learn about this later if you haven't already. And that gets rid of those zeros, but keeps those same 2 SigFigs. So, leading zeros, not significant. Captive zeros are zeros between non-zero digits, like these 2 zeros between the 1 and the 8 here. And captive zeros are always significant figures. We can't get rid of them with scientific notation, and can't get rid of them without changing the value of the number, so they're always going to be significant. And then lastly, trailing zeros, the last type, the ones at the end of the number after all of the other non-zero digits. Trailing zeros are sometimes significant and sometimes not, and what determines if they're SigFigs or not is a decimal point. If there is a decimal anywhere in the number, then those trailing zeros become significant. If there's no decimal, then all of those zeros are not significant. So we have that example of a 100 and how 100 with no decimal is only one significant figure, but adding a decimal to the end of it means that that's 3 significant figures. And we would only do that if we are sure of that measurement, if we used a measuring device that gave us exactly 100 milliliters instead of about. A lot of times when I have a 1 SigFig number, even if I don't say it, then I'm thinking about or close to or approximately. So with this 100 idea, if I had 100, no decimal, then that's about 100 milliliters. Maybe it's 99 or 101, but it's close enough. Versus 100 with a decimal, that's exactly 100. Not 101, not 102, not 99, exactly 100. And more SigFigs means more careful measurements, better measurements. And this side note that I had pop up here is an important idea that a lot of people kind of forget about along the way. It doesn't matter where the decimal is in the number. If the trailing zeros, the zeros at the end of the number, they are always going to become significant as a group if there's a decimal anywhere in the number. So like I showed you just a moment ago, 100 with the decimal at the end is 100, and that becomes significant. These 2 zeros are SigFigs. But even if that decimal's in the middle of it, and our value we were trying to write down was 10, that decimal still makes both of those zeros significant figures. Or 1 with 2 zeros after it, 1.00. That's 3 total SigFigs there. Both of those trailing zeros are significant. In fact, all of these examples that you see here have 3 SigFigs, the 1 and the 2 trailing zeros, because no matter where the decimal is, even if it's all the way up front, in front of the number, not even touching the zeros, these zeros both become significant figures along with the 1 because there is a decimal present anywhere in my number. So it doesn't matter if there's a decimal in the middle of them, before them, or after them, or nowhere touching them. If there's a decimal anywhere, trailing zeros are significant. So let's practice this. I've kind of put those summary of the steps and the rules right there up top. I kind of numbered it 1 and 2 because that's our process. find anything you're sure is a SigFig, which is generally anything that's not a 0, and then look at the rest of the zeros around those numbers and figure out what kind of zeros you got, and then step through the rules for those zeros to figure out how many total SigFigs you've got. So I'm going to start off by highlighting all of my non-zero digits. So I can already say that these are all definitely significant figures. And then we're going to look at the rest of the zeros we've got and see if those are going to add to our SigFigs here or not. So in our first example here, 1,000, and that is a comma, not a decimal, so that is 1,000. I have that 1, which is definitely a SigFig, and when I look at my zeros, since they are after all of my other zeros, those are after all of my other non-zero digits, after the 1, those are trailing zeros, and which means they're only going to be significant if there's a decimal in my number. And there's no decimal anywhere in that number, so those are not significant figures. None of them are. So only one total SigFig in this value here, which is the 1. In this next value, 2.134, I've already checked off all of the digits. Since none of them are zeros, there's no doubt those are all significant figures, which gives us a total of 4 SigFigs. So don't be confused when there's no zeros. Zeros are the only thing that's complicating SigFigs. If you got no zeros, you should have no doubts. So in this next example, we got a whole lot of zeros up in front of the 1 that we know is a significant figure. If those are to the left, leading our non-zero digit, then that is a leading 0, and these are never significant. We could get rid of those with some scientific notation. So that, once again, leaves us with 1 SigFig. And then here we have some zeros in between the 1 and the 5 that we know are SigFigs. And if they're between, they're captive zeros. Sometimes I call these sandwich zeros, and captive zeros are always SigFigs. So each and every one of those is a significant figure, which brings us to a total of 5 SigFigs with that specific measurement. And last but not least, we have a 1.000, and those zeros are trailing zeros. They are after my non-zero digits here, and that means that they are only going to be SigFigs if there's a decimal, which there is, which means that all 3 of those are significant figures, along with the 1 brings our total to 4 SigFigs. So this is the most basic skill that we need for SigFigs, is being able to look at a number and count how many SigFigs we've got. So this is when I'm going to have you go to page number 10 at the top and practice this idea. Number 1 is just like what we were doing. We got some measurements, count how many SigFigs they've got. Question number 2 is also kind of a basic SigFig question, and we talked about this a fair amount at the beginning, about why we would want our measurement to be reported with more SigFigs instead of less, so 18.0 instead of 18. I know it'll depend on our measuring device, but tell me why I would want a measuring device that would give me 18.0 instead of 18. Now, you'll notice that it says to practice and play. We do have a booklet that we can play to practice our SigFigs, and I am posting that with our review materials so that you can play that on your own if you do need more practice with this simple idea of counting SigFigs. And so now we're going to finish out the rest of page 9 with what is really some pretty simple notes about what we're going to do when we have a math problem. Sorry for that interruption. So when we combine numbers together, the answer that we get is a combination of those separate numbers, and the answer is going to need to be rounded based on those numbers that we put together to get it. And we're going to round it based on whichever measurement was the least precise. So we can make 100 good measurements, but if we do one really bad measurement with not very many SigFigs, then that could ruin all of the calculations that we have to do with all of those numbers. Now, the rules for where we're going to round our answer and how we're going to tell where to round it is going to be slightly different based on what type of math we're doing. So, different rules for multiplication, division, and addition and subtraction, as you can see below. But it's the same general idea. We're going to round it based on the least precise measurement. So with multiplication and division, we are going to keep counting significant figures, and the SigFigs in our answer is going to be determined by the measurement with the least or the smallest number of significant figures in the calculation. And you can see this in action in that first example that we've got here. I took 4.56, which is a 3 SigFig number, multiplied it by 1.4, which is a 2 SigFig number, and my calculator gave me this answer, 6.38. But because the least number of significant figures from the numbers that I put together to get that answer was 2, then I need to round this answer so that it just has 2 significant figures. And I know what I'm saying sounds different, but all we're going to do here is pay attention to the first 2 digits, just reading from left to right. The first 2 SigFigs are going to be kept, and then any other numbers are going to get rounded off as usual. And here, because that next number is an 8, then that's going to round by 3 up, which is why our final rounded answer with 2 significant figures is 6.4. So this is just like if your teacher had told you to round this 6.38 to 1 decimal place. The rounding process is the same. You still find that place, okay, first decimal, and then you look at the next number, decide if it rounds up that last number that you're keeping or not. The only thing that's different with this is the words that I'm saying. I'm telling you to round it to 2 SigFigs instead of round it to 1 decimal place. So it's a little more flexible. You have to do a little bit of looking to figure out your SigFigs, but it's not going to be as different as it right now kind of seems to be. Now, most of what we're going to be doing is multiplication and division, so it is going to be a lot of SigFigs in your life moving forward. But if or when we do addition and subtraction, it's actually going to be the number of decimal places that matter. We're still going to be rounding to the least number of decimal places, but now it's just kind of old-fashioned counting decimal places. How many digits past that decimal were there in our original numbers and in our final answer? So you can see here, if we're adding together these 3 numbers, 12.11 has 2 decimal places, 18.0 has 1, and 1.013 has 3 decimal places. So even when our calculator gives us out this answer, our final answer is going to be rounded to 1 decimal place because that's the least number that we started with. And so this number rounded to 1 decimal place is going to be 31.1 because the 2 does not round the 1 up. It's not big enough, so it just stays 31.1. So when we do math, look at the numbers you put together to figure out where to round your answer. It's either going to be based on SigFigs or decimal places. Mostly SigFigs, but you should never technically have to ask me ever again, where should I round my answer? If you do ask me, I'm going to respond back with, well, how many SigFigs did you start with? And have you help me reason yourself through where we should round that answer. So there's a quick little kind of detour talking about exact numbers before we see this in action with those problems at the bottom of the page. This will really come into handy more when we start doing dimensional analysis and some other calculations, because there are some numbers that are going to look like they don't have any SigFigs, but they actually have infinite SigFigs. So these exact numbers that we're talking about have an infinite number of significant figures, generally because there's some kind of standard, or they were determined with some super precise counting or experiments. And the best example I can give you is counting people. If I tell you that right now there are 5 people in my classroom, I shouldn't have to tell you or write down that there are 5.00000 infinitely repeating people in my classroom. I shouldn't have to write all of that because I hope that you know if I counted, it's small enough for me to count on my fingers. There's 5 people in this room right now, that there's not any little bits or pieces of people being hidden in any cabinets. So this 5, I can just write or say as 5 people, and if it is known that it was determined precisely, this is a simple example, but there are some experiments and conversions that we can use that are ultra precise like this, that I can say 5, and even though it looks like one SigFig, this has an infinite number of zeros coming after it, 0.00000, and we're never going to treat it like a one SigFig number or round our answers based on it, basically. Another simple example that you might relate to is the fact that 1 foot is equal to 12 inches. That's the way a foot is defined, is by being 12.00000 inches, and it's not 1-ish feet or about 1 foot. It's exactly 1.00000 feet equals exactly 12.00000, infinite zeros there, inches. So we don't have to show all of those SigFigs to understand that this constant, this rule is not something to round based off of. So let's do some practice calculations. And before you start plugging away at your calculator, I've actually gone ahead and done that part for you. So these are the unrounded answers here. These are not our final answers. But I would encourage you to go ahead and write them down, because here, and only here, I'd like you to kind of show yourself, your future self, for when you're confused and come back and look at this, what you got out of your calculator, and then what your true final answer should be. And so what I'm going to do first is look at the math we're doing. This is 5 times 6. Since we were doing some multiplication here, then we are going to be counting and paying attention to our SigFigs, not decimal places. And so if we're paying attention to SigFigs, 5.000, these are trailing zeros, so this is 4 significant figures, and this is 3 significant figures. And so when I'm trying to decide how many SigFigs to keep in my answer, we're going to keep the least number of SigFigs. So we need to make 30 into a 3 SigFig number. And most of the time this isn't going to need to be happening, but it does happen occasionally. We need more SigFigs. Right now, 30 as it's written is just 1 SigFig. So I know I could probably put a decimal at the end, and that's going to make that 0 significant. So now this is 2 SigFigs, but how do I get another one? Well, we're going to have to add another 0. And both of those zeros are SigFigs because they're trailing zeros, and I've got a decimal. So 30.0 is actually how I would expect you to write that final answer, to show the level of precision, the amount of care we put into these measurements. We took a lot of care to get all those SigFigs. We don't want them to disappear just because our calculator doesn't understand how much effort we put into getting those SigFigs. Here in this next problem, we have a much longer number, and if we look at the math that was happening here, this is multiplication and division, so even when they're combined, those are still both SigFig operations, so we're going to count the SigFigs in each of these. No zeros to be questioning about in that first one, so that's 4 SigFigs. These sandwich zeros are, of course, always significant, so that's also 4 SigFigs. Those leading zeros are not significant, so this first number on the bottom only has 4 SigFigs. And then this last number has 3. The leading zeros are not significant, but that trailing 0 is. So, like I've said before, one bad measurement, one number with less SigFigs means that's going to determine what we round our answer to. If they were all 4, then we just round it to 4 SigFigs. But because even one of them is 3, we've got to round this number down to 3 SigFigs. But we just start from left to right. These are the 3 digits we want to keep. And in this situation, also kind of an edge case, not something we do a whole lot of, but something you should be ready for, is that I can't just keep the 532, because this is a completely different number than 532,324.79. This is 1,000 times smaller than what I want it to be. So anytime that we round off digits between the SigFigs and our decimal, you have to remember to replace them with zeros. And those are going to become trailing zeros, so 1, 2, 3 of them here. So as long as we don't put a decimal at the end of this, this is still just 3 SigFigs. If I put a decimal at the end, that becomes SigFigs, way too many. But without the decimal, those are just placeholders. So 532,000 is our closest, best rounded answer here. Now, looking at this, I've actually noticed that I think there is a typo in what I have written on my screen, so there's probably a problem with this answer. If you just want to fix yours to make it match mine, really what we're focused on here is the rounding of the answer, not the button pushes, but obviously I have failed at the button pushes in my calculator somehow. But let's go with it as if this was all fully correct. We are doing division here. So we are still going to be paying attention to SigFigs, and our number up on top has 5 significant figures, and this scientific notation number on the bottom actually only has 3. One of the things that we'll talk and learn about later with scientific notation is that only the numbers in the base, the part before the times 10 to the something, are SigFigs. So 2.00, that is 3 SigFigs. So I need to round my final answer to have 3 significant figures. Just want to keep the first 3 digits, and the 0 will not round my 9 up, so this will just stay 27.9. In this last example, we are adding, or I have already added. So addition and subtraction is actually going to be decimal places, finally, instead of SigFigs, but we still have to count and pay attention to how many we start with so we can round our answer accordingly. Here we just have 1 decimal place. Here we have 2. So my least number of decimal places is 1. So I'm just going to be rounding this to the first decimal place, and that 7 will round my 3 up. So 999.4 is our final answer. Hopefully this isn't too bad. I know it sounds weird and it's different. It's something to get used to, and I'm sure you don't need one more thing when it comes to doing calculations and numbers and stuff, but it really does give you more power over the meaning behind these numbers. So if you haven't already, then the problems that go along with this are on page 10, and down here at the bottom half, 3, 4, 5, 6, and 7, we are going to do, but I don't need you to do this pink highlighted part. These B, D, F, H, and J parts on numbers 3 and 4 can be extra practice. They are not required. You can turn your packet in without having touched these or after scratching them out, and you can still get a 100%. So I never need you to do these pink problems, but in case future you needs some problems to come back and try before the test, some of these could show up on the test. You absolutely should be able to do these problems, but I don't think that it's worth you doing 10 problems. If you can handle the first 5, then I think you got it. So I do need you to do all of the blue highlighted problems here, and the answers to 5, 6, and 7 have been posted on Canvas. Or come in and ask me if you're confused. It's probably not the math that you're confused about, so you need help understanding why you would round it in a certain place. So come in, ask about it, let me help you understand these better. I know that it might not be perfectly clear right now, but hopefully after we do some more with it, you'll help. It will help kind of figure out what's going on and why we care more about some numbers than others. So that's all.